Hey, welcome everybody. I am Mike Mensch, Business Development Manager at Princeton Consultants. Thank you for joining our webinar today about practical strategies and best practices for making optimization work in production with Gurobi. Our webinar presenter today is my colleague, Dr. Rob Randall. We are planning to go for 1 hour. I know a number of you are still joining, which is great. We are leaving time for questions at the end. Post your questions in the Q&A and we will get to them. Please note that we will send copies of the slides afterward and we will post a recording. And I will now turn it over to Rob.
Hi, welcome everyone. Today we're going to discuss some real-world examples of production models that Princeton Consultants has built over the years, um, and talk about how it's not just raw performance, not the machine, but formulation, tuning, architecture, or where the performance really comes from. We're talking about 6 lessons today. Each has been proven by real project work. Um, We'll talk about some of the areas in a minute. So a little bit about Princeton Consultants. We've been in business for more than 40 years, more than 1,800 projects delivered into full production, and over 2.4 billion saved through optimization. It is, in fact, that was a project that a colleague worked on, which is an informed Edelman finalist for the census. But we've worked across many industries from energy and transportation, e-commerce, government, healthcare, and finance, and have been able to deliver savings and successful projects in all of those verticals and many more, in fact. Um, so a little bit about me. I've been with Princeton Consultant for almost 20 years. It'll be 20 years in September, in fact. Building custom optimization models, decision support tools across many different types of transportation. I think I've touched almost all of the major ones, rail, truckload, trucking, less than truckload, air, and shipping containers, um, energy, and e-commerce. Some of my recent focus has been on performance and scalability of large-scale models. We've done a lot of solver tuning, reformulation, and storage, and integration at scale. So a lot of times we get projects that come from models that are already built, and they ask us to see if they found they have issues and need help. So they bring those to us a lot to work on, in addition to the full life cycle development work. Some of my current work also spans airport revenue, so the air side, veterinary maintenance optimization, energy grid optimization, clinic patient scheduling and healthcare, and other optimization fields, including fractional and airlines. I've been fortunate to be on projects and been a 2 times informed Wagner Prize finalist. The first was for a bulk chemical dispatch model at Schneider, and the second was for e-commerce optimization at Birchbox. I am a senior member of Informs, and I'm past president of the Clemson University Industrial Engineering Advisory Board. I got my PhD in industrial engineering from Clemson. Go Tigers. Okay, so the prototype, the prototyping and production are two different things, right? Um, Production often runs on a clock. A model that doesn't solve or is late is wrong. It doesn't matter how good an answer you end up getting after the clock expired. It's like playing basketball. If you don't let the ball go before the buzzer sounds, it doesn't count. And then changing data. It's really easy to tune a model, a prototype model, when you have a static data set and you don't have to look at anything else. You just look at the data set and you build the model to that data set. However, in production, inputs change every day, every cycle, whatever, based on the frequency with which you solve. Um, we're learning that a lot in one of the projects I'm working on currently, which is for clinic patient scheduling. As the new clinics roll in to the project, we get data that we haven't seen before. Some of that is breaking the model, some of it just makes it solve slowly. So those are things we have to take into consideration as we continue refining that model and that system, that we get these new data sets and new structures that we haven't seen before. The next, scaling, you get new resources, new products, new locations. Some of these are combinatorically increasing the number of variables and constraints in the model. That can really affect the time it takes to solve. They're not, most of the models are not linear. And then lastly is maintainability, right? You want these models to run for years, um, but you don't, it's not just going to sit there and run. Someone has to debug it and extend the model and make it better, add new constraints, add new features that the business wants. So clarity in your code and in your design is a production feature. So these four pressures motivate all the lessons and discussion we're going to have from here on. So here are the six topics we're going to cover today. So the first is model the right problem before you choose the technique, right? So make sure you know what the problem the business wants needs you to solve, and don't just build a model for building a model. Um, Formulation will often beat hardware. There are many things you can do to a formulation to make it solve faster, other than just buy a new computer that has more cores or a better CPU or GPUs. Um, Sometimes you have to reformulate the model, decompose it, and you have to understand how that affects the solve time, and understand the structure of the model so that you can understand how to reformulate it. Um, then we're tuned to the model, right? We're going to define what good enough means to us. So we have models that have to solve under pressure. We need to make sure that we know how to get a solution every time. Then the model architecture determines how scalable the project is. Things like warm starts and staged build of the solver versus restarting from scratch. It lets you do those kind of things. And then lastly, um, validate and engineer production. You're not building a one-off prototype. You need to build something that can run without you touching it daily or hourly or minutely, whatever the problem, whatever the problem is. But the performance comes from the model, not just the machine. We're gonna go through a kind of a running example coming from a uh, energy grid problem, but the lesson is framed across many industries that we've worked in and validated these lessons from. So our example is a grid on a hard clock. So there are several independent system operators in the United States, and they have to determine what generators to turn on commitment and how much each should produce dispatch. So in these problems, there are thousands to millions of variables and constraints. And they have to be solved very, very quickly, because from the time that the energy producers put in their bids for the hours until when they have to award it is a very short period of time, often less than 30 minutes total. Um, so if you can't solve in that window, you can't actually assign who's going to run the power for the day, and that's not good, obviously. Then things like energy storage, batteries. They can check. They can they have multi-state. Um, they are multi-state, right? They can charge, they can discharge, or they can sit idle. Where the traditional generator is either on or off. There's no storage part of it. So these add combinatorial complexity to what we're trying to solve. So the key part of the generalization here, right? So we're talking about a very specific case, but it's very generalizable. It's a very large mixed integer structure. We have a hard runtime deadline, and then complexity grows, right? When we add new resources, and it must run every day. Okay, so this is kind of the example what happened when you added these energy storage units, the batteries. So when we add the baseline, it was taking about 90, 94, 95 seconds to solve. And you start adding more of batteries, we end up taking 20 minutes. That does not work very well when you have a very short window to solve in, because these have to be solved repeatedly because there's some other constraints that are outside the model. So sometimes you have to resolve the model to make sure that it's actually feasible for the transmission constraints that are non-linear and not often, or at best, are approximated inside the model. And then there's other work done on them outside the model. So the first thing you have to do um, is make sure that you're modeling the problem correctly before you pick a technique. So we're actually going to go to a different project, different client, to kind of understand what that is. So we're working with a company who was trying to create a hardware accelerator to solve problems. So basically, move things to the chip itself versus software. So they came to us with a problem. They gave it to us with it came in a QBO format, quadratic unconstrained binary optimization. So, and they were big. They were huge precedence dependencies on per instance. And if you just looked at the QBO, you were like, I don't even know what this means. Like you couldn't figure out what what the problem really was, which was the point. They didn't, they were just trying to solve a problem, a generic problem. However, what we realized and what we were eventually able to do and handle the problem was that we noticed that it was actually um, a resource constrained project scheduling problem, just a traditional scheduling problem. But even all that, it didn't solve very well. About half of the problems couldn't solve within like 6 minutes. However, what we ended up doing, so we had to understand the business problem, then understand the data, and then we understood the model. And what we did, we found the structure that we found that there were each of the decomposed into bipartite subgraphs, and each of the subgraphs could solve very easily. And then all we had to do was break those apart using MIP to solve the task group, and then create the RCPSP and use a generic CP solver that could handle it very easily. So, I mean, we went from the problem was the client didn't love it. They liked we found the answer. They didn't love the answer because their goal was to create hardware to solve the problem. And when we actually solved it with Gurobi and a CP solver separately, we solved the CPs in about less than a second each, and we found the MIP solved in a few seconds total. So we were able to find full solutions in like 5 to 20 seconds total. So that it ended up not being the right problem for them to be able to create a hardware accelerator. No one was going to pay, the kind of money you need to recoup that for a problem you could actually solve in, a few seconds on regular hardware and software. So that's one case. So then the next lesson, formulation will beat hardware. I think it's maybe an interesting take, but we're going to show in a minute that we can rewrite some math that will create improvements that just buying a faster machine is not going to fix. So the first is a very simple constraint, and we've all written this constraint 1,000 times, 100,000 times, I don't know, a million times, and that is a big M constraint, right? So in the case of our independent system operator, you cut a generator, the power a generator produces has to be 0 if the generator is not on, and then it can go up to the maximum megawatts that a generator can produce if it's turned on. So on the left, you see a very intuitive rule, right? Truly a big M, some number bigger than any value that it can take. Well, the problem is that creates a very loose LP relaxation. So you end up in a very big search space before you rule the options out. The version on the right creates a much tighter bound. So if you set the big M, in this case, big M being very loose in this case, not very big, but what it is that generator can only have 200 megawatts of power at the capacity. So technically power is always less than 200 times is on because you can't go more than that. So this creates a much tighter bound in the LP relaxation and better bounds, and then you end up using fewer nodes. Um, so this is a lesson you can apply in any domain, any um, practitioner can apply it because we do this every day. These are very traditional constraints in almost every model. Is you have a indicator variable, and then you have something that is set off of that indicator variable. So some of the patterns um, we come to again and again. We just talked about the first one. Don't just use a generic big M. Use a value that makes sense in the situation. The next would be removing redundancy, the things that add work without changing your feasible region, which a lot of which Groovy will do in some cases in the pre-solve, but sometimes it can't tell quite as easily as you and I can tell when we know what we're doing and know what the model is actually building. The third is breaking symmetry, right? We see this a lot. We're going to go through an example of it in a minute, but another one where we see it is um, in some clinic scheduling stuff we're working on where the model doesn't know the difference between one treatment area and another treatment area. They're just two areas that can be that are treatment specific, or it doesn't know the difference between one person working in the clinic and a different resource in the clinic. So there are ways you have to build the constraints to break these symmetries so that you push it to find solutions that don't repeat themselves. The next is decomposing it. And again, we'll see an example of that very shortly. That became one of our Wagner Prize finalist work. But when you have a hard model, sometimes you have to understand the format of the model and the can you find a subproblem that you can solve easily that you can then stitch back together in some way to build the full solution. One we've done before was definitely in trucking. We did a lot of work on breaking a problem apart so that we could build the trucking schedule also. Sometimes it's about curves, right? Using piecewise linear instead of more fragile curves are very good. Some curves can be very brittle. Obviously, very common in energy cost curves or storage efficiency. Then lastly is tie in the domains. Don't give, don't allow just a very, very wide value. Make sure that you know what each variable, um, what the output can be, the honest range of it. Uh, you know, so in general, one way we like to think about this is that optimization modeling is not just a mathematics technique, and not just a software engineering technique, but it's kind of the combination of the two. It is software engineering plus mathematics. So that's how we like to frame all of the work we really do, is that we're not just building models, we're building systems. And we take the principles of operations research and optimization, and also the principles of good software development, and blend them together to create systems. So our third lesson here is when the structure fights you, sometimes you have to reformulate it and decompose it. Sometimes, winning is not a tighter constraint, it's a different formulation entirely. So the classic example of work we've done here of this was Birchbox, which you can read about in the Wagner Prize final paper that was published 2021 or something. So Birchbox at the time was a cosmetic subscription box company. They shipped cosmetics in boxes to subscribers. So they had hundreds of products, thousands of subscriber boxes. They were trying to honor different pairings and exclusivity and inventory rules. But what happened was they had a model built by a data scientist. Because part of the work was actually done using machine learning to do a bunch of the inputs and grouping subscribers into smaller cohorts. So you didn't build a box for every subscriber; you build it uh, into a group of subscribers, basically. And what happened was it started taking forever to solve, 30 to 50 hours. Um, and sometimes you couldn't use the whole answer at all because it couldn't it couldn't even it didn't fail fast. It took forever for it to even determine if it was feasible or not. So that was a big issue. And two of the main culprits were symmetry, right? So box contents, if you had product A, product B, product C, product D, and product E, if you listed them in any order, that's like five different, five combinatorial answer. But you could do those in any order, and you had different solutions, but there's the same solution, there's the same box. So that would create some really big symmetry issues. And then the other issue they had were they were trying to do a blended objective. They were doing one weighted sum of several different objectives. And we tried some quick fixes. We tried perturbation, symmetry cuts. It just didn't help. And the opportunity here is they could not even test new rules they wanted to include because they couldn't get a solution fast enough. So speed was not just a nicety; it was a business case. So we created a brand new technique for this. It was powered by column generation and the the ability of modern MIP solvers. This was a Gurobi. This was built in Gurobi, in fact. So it was the Gurobi solver. Um, so we framed boxes as patterns. So we were able to create subproblems to get valid box configuration on demand. So we never had this issue of having the products in different orders creating different solutions. So then, instead of like a traditional branch and price or column generation approach, it was not just an LP each time. The master restricted was not just an LP; it was actually a MIP. So we were able to do pre-solve, heuristics, cuts, and then when you added patterns, instead of just adding columns, you actually sometimes you added rows and columns. Again, that would be a twist on standard column generation. And then from there, blended, we created hierarchical objectives, feasibility, then box count, then the product minimums. And we were able to do all of this using modern software techniques of not having to fully rebuild the problem every time, um, and solving on small node limits and warm starts. Um, all of that allowed for a big difference, right? So we went from taking days to solve to roughly 10 minutes. So 99% plus reduction in runtime. And Dave Bendaz, who was the sponsor on the Wagner Prize Science paper, who was at Birchbox at the time, called it life altering. Our fourth lesson is tune to the model, define what good enough is, right? Is optimal required or is there a good enough value? Um, and many times, Gurobi's default parameters are very good and a very good starting point. But sometimes when you run the same problem over and over again, you see um, tweaks you can make to it, not just the defaults. So in real world data, we're looking at new data every day. Um, but often the data has the same structure every day, even though it's not the same. So in the case of like the battery example before, we were able to create a testing framework that we took and used. We were able to use different parameters over and created a whole system where we could uh, benchmark different values and we could retune as our workload evolved. So again, tuning is an engineering, not a one-time thing. So some of the parameters we were able to use were pre-solved, changing the values there. Um, we were able to change the MIP focus value for uh, one of the model types is actually uh, quadratic objective MIP. And we were able to tweak the relaxation version. We used, I believe we changing it from primal to dual simplex. Might be the other way around now. Don't remember off the top of my head. What it allowed was it changed. It reduced the runtime significantly doing that. So again, tuning is an engineering discipline, not a one-time setting. So Um, optimal enough, right? What does that mean? So as we said earlier, right, solving the optimality but getting it too late is not does not beat optimal enough and on time. So a lot of the clients we work with, they all originally said they wanted it optimal, and we're like, okay, we like that. We're mathematicians too. We like optimality, improvable, but what happens if we gave you something that's like, you know, $500 worse, but it took, 1% of the computing power. And guess what? It came back in, 5 seconds versus 5 minutes or whatever the actual math would be. I guess it'd be more than that if it was 1%. Um, so in this case, we had an e-commerce client. They wanted to sign batches of 500 to 1,000 orders to the fulfillment center around the clock. Every time they get 500 or 1,000 orders, they assign them. Um, and what we found was for the general orders, the general batches, we could set a MIP gap at 50, and the solution was good enough for them. The difference didn't matter so much that they were going to wait to handle the rest of the solve. Then we had some sensitive ones, much smaller orders generally, and we kept a tighter gap. So tolerance again is a business decision, is set per case. So tiny defensible gaps turn, we've all seen model solve, right? They get a very long asymptotic tail between what the best solution is and what the best bound is as you're trying to prove optimality. Um, so we turn that long tail into throughput. We get the model solved, they get the work done, and we start over and do another solve with something else. So we just keep doing work for them. Again, my basketball analogy: if you don't get the shot off before the buzzer, it doesn't count. So sometimes you got to get the shot off. So our fifth lesson here is architecture determines scalability. Sometimes you design your workflow to solve incrementally, and sometimes the solver and the same solver will go much further if you do it that way. So in the old days, I'm getting up there in age. We use tools like, as an example, Ample, right, or Opal, or many of the other tools at the time. We built models in. You built the whole model, you solved it, and if you needed to iterate, you had to build the whole model again and change data inputs or change constraints. So the way to think about this could be, well, you build the whole house, you want to do something else, you tear down the house and you rebuild the whole house again, right? So you want a deck, now you got to tear down and build again. Every run starts from zero, even though most of the answer or even most of the problem didn't change. So in modern software and with Gurobi or any of the major solvers, now you could build a house and then add the garage and start from where the house already was, and then add the deck, and you keep what you already solved between warm starts and staged model building. You can do all of this without having to start over. Now now you're doing this under pressure, right? Under a deadline. Which way would you choose to build your house? So the example here of one of the project where this happened was we were working for an ISO, same ISO, and they were looking at their capacity expansion model. So not a daily model, but it's a long-term model which answers billion-dollar questions. Which plant do you build? Do you use which transmission lines to use? What storage units to build? Where to build them? So before, when they first had it, it was very slow. So the planners could only test a handful of cases. And then so they asked us to take a look at it. And that's what they were doing. They were building the model, solving it, changing a few inputs, building the whole model again and solving it. So what we came back with was, okay, in in Python or in any language that you work with, and with Gurobi, you can build the model object, you can build the whole model object, then you can solve it, then you can iterate using that same model object by either changing the coefficient of the variables, adding new constraints, removing constraints, and then just resolve using the already, what you already have. So what we were able to do was take something that took them 4,000 seconds, so an hour and almost hour and 10 minutes or something, if I'm doing the math in my head right, down to 3 minutes. And almost all of that is actually in the first iteration when you're building the model. The model itself took about a little over 100 seconds to build. So, building the model itself is very, um, it's actually a fair amount of time to actually process the data. It was a lot of data on a very big model. Um, so actually building the model took about a little over 100 seconds. And then we were able to solve the whole thing from after solving the first iteration in 150 seconds. We were able to solve the other 21 iterations by changing just the constraints and just the coefficients we wanted to change in roughly 30 seconds. So this was obviously very um, life altering for them. They were able to go through many, many more um, scenarios, right? So that you can make sure you're making a confident decision in what you want to do long term. So that was a big win for them. Then our last um, bullet or last lesson here is, uh, validate in your engineering is for production, right? A model in production is software. So we need to treat it with the discipline that software demands, production software demands. So, there's a bunch of hygiene you do here for debugging and reproducibility. So you can keep your parameter files versioned so that you can change, just the parameters. You know what you've changed over time, which is very good. And just like you do in any other configuration for software, right? You don't just hard code them in the code somewhere. You put them in a config file. And Grovia itself had their own parameter file, PRM. If you build it as part of another system, you could also just put it, in your JSON or XML or however you build config database. But you just don't want it hard coded in the code. You want to be able to know what's in there, make it easy for A/B testing of settings, and a clear audit trail for what has changed between runs. Definitely should export the model. In general, we recommend MPS because of the much more compact formatting of the model versus LP. LPs are more human readable, but obviously you can get a lot more data in an MPS file than you can in the same size LP file. So but you definitely want to keep an artifact of every solve if you can, so that you can debug it more easily. Readable variable names, not just X. Just don't name your variable X in the model unless you have really, really, really good documentation somewhere so that someone who's analyzing the file in the middle of the night can know what X is. So you want to know, don't call it X123 or X12, X13 instead of assign order 1 to machine 3 or assign 1 to distribution center 3 or whatever your IJs are in this case. You want to guard solutions, guard integrality. If you need it to be an integer, you can set what an integer of feasible tolerance as an example. We use that on several projects where we have some clients with some bad data practices in general. Couple that have between the biggest number and the smallest number in the model are somewhere in the order of 14 orders of magnitude or 16 orders of magnitude. Obviously, double precision is not great on that big orders of magnitude. So, we have to work with them to make the data work better for modeling in general. So there are lots of things like that you have to work on. And then again, back to one of the first things I talked about was the honest bounds on your variables, right? Make sure that your variables are the upper and lower bounds on your variables are legit. Don't just leave them 0 to infinity. Don't leave it to the solver to have to use constraints to figure out what a true bound is on the variable. If you know what they are, give it to the model in advance. That'll help it pre-solve and help it solve faster. It'll shrink your search space. Um, and then maybe this should have gone first, but really make sure that the formulation is documented. It's just like any other software, right? You need documentation. Again, this goes back to the idea that production modeling is production software, and it needs to be it needs to be formatted or formatted. No, it needs to have notation in the formulation so that you know, if I leave Princeton, someone else could pick up a model that I've written and now, or if I leave the project even, someone can pick up the model formulation that I wrote and they'll know what I meant and make sure that my code says what I meant it to say. That's also a big issue, right? When you're writing code, the solver does what you tell it to do, not what you wrote down in a mathematical formula somewhere else. So it helps with code reviews and debugging the code to make sure that what you said in the math is what you implemented in the code. So it exists in two different places. So those are very, very important. So sometimes you need someone to independently review your code or your model, and it pays off in debuggability and reproducibility. So again, this kind of goes back to what we were talking about just a minute ago with being, so production system. So when you test a production system, right, when you're upgrading a model or you're upgrading software, you test it. You test the upgrade. You verify that it does what you want it to do. So when we had a client moving from Groby 9, which is badly out of date, to 13, we did a lot of production models, so real production runs against hundreds of scenarios. But we took this data, solved it in 9, solved it in 13, make sure that they're finding the same solutions. And this client uses duals for a lot of things also. So we were having to pull the duals out, making sure that even those matched, which was fun. Sometimes they didn't because you found a different optimal solution, even though they were close. So we had to make sure that they were, both optimal, had the same objective value, just because we went down a different path. So we validated it by case before shipping relationship anything. Oftentimes upgrades will find hidden algorithmic issues. They'll fix them, not just the raw speed. So that is one of the reasons to stay current. And one of the things we explained to them about upgrading, not just from 9. They originally just wanted to go to 13.0, and we're like, no. If you can go to 13, go to whatever the newest version of 13 is when you get ready to actually upgrade. Because that's going to be the one that has all the bug fixes in it already. Like whatever, it'd be 13.01 or 13.11, something like that now. So those kind of things exist in the data. So you need to change, when you're testing it, you want your mission critical systems, right? You need to change, you have to make sure you earn the trust before you do the release. And they had a bunch of stakeholders who really wanted to make sure that nothing was going to happen when they upgraded. So I added a +1 lesson here. So let's tie it all together, right? So across all of these engagements, the biggest gains we saw were not from the raw horsepower of a computer, but from understanding what the business actually needed to decide, and taking that knowledge and expressing it in the form that the solver can use. So really, it's not just deep optimization expertise, which we have, and it's not just deep operational knowledge that we've acquired over years in many different industries. Neither of those are sufficient alone. What you really get and where it comes together is where they meet, is this meeting of optimization expertise and operational knowledge. And we have our standard practice is you understand the business problem, then you make sure you understand the data that you're given, and then you build the model. You don't build the model before you have data. You make sure that the data you have is something you understand, you know what it is. And we have all of these great anecdotes of just data, data sent to us. Some we, with the title says, you know, travel in hours, and it's not. It's travel in like minutes or seconds that they give us. So you have all of these things that you have to make sure you understand before you just plug it blindly in a model, and then the model blows up because you didn't understand what you were giving it. So those are kind of um, some of our very, some of the takeaways that I have, and some of the lessons we've learned over the years at Princeton. So again, the 6 lessons here were model the right problem, right? So we had this hot, our hardware accelerator. They gave us a Kubo that was really an RCPSP. Formulation beats hardware. You can tighten it, tight bounds over versus the generic big M. Sometimes you have to reformulate and decompose. So Birchbox, in our example there, went from days to minutes to solve. Tune and define good enough. So grid e-commerce was our example there, right? So model specific tuning, on make sure you know what you're looking at. Architecture determine the scalability. So right, solve incrementally, don't rebuild the entire problem. Build it from add on, don't rebuild. Then validate and engineer for production, review, test, reproduce, format, create notation, create formulations, document. And then if there's some other things, there's also Informs has good resources on all of this as well. They have a whole system on that. They have uh, their the Informed Analytics framework that we helped Irv helped build from Princeton. So they think a lot about this as well. We've been doing this, and we've been working on that framework long before the framework existed, and they built one, and it's very similar to the thought process that we've been using at Princeton for many years on how to build production software and build production models. So then one fun thing, maybe looking ahead, uh, is the idea of optimization and AI, right? And we don't think in my opinion, AI is not going to replace Gurobi. It does not solve things like that. That's not how AI works. But what you can do with AI is help build systems around the model. It can help you sequence models and route scenarios. Uh, it can help diagnose infeasibility and explain why there's infeasibility there. And not just to me, right? As a modeler, it can help a user understand why something might be infeasible. And that's kind of important, right? Nobody likes getting the call at 3 a.m. with the model's infeasible, and it's always because they gave it some kind of bad data. It's never failed. The data we did, as good as we try to be about data cleansing and data capturing, there's always some new piece of data that gets sent to a model that we haven't thought of yet. That happens in the real world every day. I can't tell you the number of times working on a airline project where they do the scheduling at like 2 or 3 in the morning, I get a call, and it's because some piece of data came from their production system that was bad. That they didn't harden their production system to handle the data correctly. That we were assuming they were not going to send us bad data, but they did. And maybe we can have an AI agent help figure out and fix it for us, instead of us having to truly test every case for just us. So maybe we can work on that. And then again, maybe we can use AI agents to help suggest solver settings based on past runs. And then help explain results, right? Monitor drift in the models. Why are things changing? So there's certainly, in the future, as we go forward into the AI age, of integrating AI agents into model solves. And we're currently working on that in some other business cases and use cases with other clients. But the mathematics of the model will play the core. I mean, you still have a decision solving engine that does this. And that's what I have for you today. I guess Mike might have some questions now at this point.
Okay, thanks, Rob. Let's start with there is a question. I'm going to make it live, but I'll read it first. In the case, Rob, where you built the model incrementally, reducing the time from 4,073 seconds to 184 seconds, was part of the bad performance due to the use of a modeling language? If so, did you convert the application to Python?
They had actually written in Python. They just didn't, they wrote it as if they were using a language like Ample, where you built the whole model, solved it, and then you started over. They just looped, they built the loop outside of the actual Python model object of Gurobi. And so you created a new model every time. Um, so the framework was there. They just didn't quite take, they didn't use the full power of Python and the solver to take advantage of that incremental solving.
Interesting. If anyone has a question, you can post it in the Q&A in the bottom uh, of your dashboard on Zoom. We'll wait a little bit.
Mm.
While we're waiting, I'll say that so this is part of our we have a series essentially best practices working with Gurobi. We will be attending in September the Gurobi Decision Summit in Las Vegas. I encourage you, if you haven't, if that's not on your radar, you want to check that out. We've been there a number of times. It's a great event, great, very educational, great client stories. So I encourage you to check that out. Again, we will be there. Yesterday, we had a new blog post by Rob and my colleague Irv Lustig. He had moderated a workshop at Informs on GPUs, so real frontier kind of stuff. And Gurobi, Ed Klotz from Gurobi was one of the panelists talking about his experiences in testing GPUs for highly complex LPs. So that's on our blog at princetonoptimization.com. It's being read, as we speak by specialists around the world if you're interested in that kind of cutting edge type stuff. So just putting out there like what we're doing, trying to advance the practice of optimization, both in a practical applied way, as this webinar was about, but then also in kind of like a forward-looking way as well. Rob, there are no other questions, so I think what we're going to do is we're going to say thank you
We
very
got
much.
one.
Go ahead.
We got a question. I saw just popped up.
Oh, there's another Q. Oh, you're right. For the approach you took for the Birchbox problem, did that involve using Gurobi's callback features to add the columns and cuts?
Yes, we used several callbacks, both to check solutions, check runtime, see if we were getting. One of the things we've been very keen on adding in solves are this idea of hunting, especially in interim solves. So if Gurobi or the solver don't find a new solution in a certain amount of time, we will just take it as that point and then iterate again. Because we know that's not the final solution anyway. So if it hadn't found something better within, 10 seconds, 15 seconds, or whatever, some number of seconds, we can then use that callback to end the current solve, iterate, add, in the case of Birchbox, we'd be adding new patterns, new subproblems to the model and resolving. So we definitely use callbacks a lot, both in on the birthmark problem and in many others.
Okay, very good. Okay, any more questions? Um, okay, we don't have any. So Rob, thank you so much. And we'll look forward to seeing everybody again real soon. And we will be sending out the slides and recording shortly.